Okay, this is the 6.7/6.8 notes. Essentially, these are just applications of logarithms and exponentials. Um, just starting out, we have to look at some formulas. So in dealing with finances, you have either simple interest or compound interest. Simple interest means you get interest on the principal that you put down, and that is expressed over a certain length of time and at a rate. Now, compound interest is when you get interest at intervals throughout the loan. So in compound interest, the very first time they compound, you get interest on top of your principal. The second time they compound your interest, you get interest on top of the entire total, which now includes some interest that you earned before. So if you're borrowing money, that's bad, but if you are investing, that is good. So this is the formula for simple interest, I equals PRT, and this is the formula for compound interest. A, which is your future value, equals P times 1 plus R over N to the NT. And then this just shows you that this part right here, if you let this go on so that you are compounding more and more and more, you notice a trend. There becomes this number at the end, which is E. So they call that compounding continuously, and we'll look at the formula for that in a minute. So yeah, it's down there. So let's do this first example. It says a credit union pays interest of 2% per annum, compounded quarterly on a certain savings plan. If $1,000 is deposited in such a plan and the interest is left to accumulate, how much is in the account after 1 year? So we need to talk about what we know. $1,000 is the amount that was invested, so that's P. The rate needs to be written as a decimal. So remember, you divide this by 100, so that would be 0.02. Time is 1. And this does say compounded quarterly, which means this is not a simple interest problem. So N in the formula for compounding stands for how many times does that happen in a single year. So quarterly would be 4. So if we plug this into our formula, so I'm just writing the formula down, and I am sorry, I'm still suffering from the laryngitis, but we're going to do the best we can. So this is 1,000, and this would be 1 plus 0.02 divided by 4, and then 4, and then this is for 1 year, so T is 1. So it's pretty much just to the 4th power. Let me get my calculator. So 1,000 times, parentheses, 1 plus 0.02 divided by 4, close parentheses, raised to the 4th power, hit enter, and it's 1,020 and 15 if we round. So 102015. Write that down. So that means that for that 1 year, we actually accumulated about $20.15 in interest. So again, all of this is understanding the formula that you're using and plugging in the pieces that they gave you. Now, if you wanted to compound continuously, which means almost like every millisecond of every day, it's just so great that it actually approaches E, then you use what we call the PERT formula, where notice that P is still the principal, E is the special number on your calculator, and then R and T are your exponents on that. So let's look at an example of this. Using continuous compounding, the amount A that results from investing a principal of $1,000 at an annual rate compounded 10% continuously for a time of 1 year. So 0.10 is my rate. My principal is 1,000. My time is 1, and I'm using the PERT formula because of the word continuously. That's the only time you can use this formula. So A equals 1,000, E, because E is a number, to the 0.10 times 1, which will just be the 0.10 power. So 1,000 I have to do this backwards. Most of the time you would hit the E button first, but on this calculator it is backwards. So I have to do 0.1 for the 10 to the E power, or E is the base, sorry. It's just the calculator makes me type it in that way. And then that gives me 1,105.17. So 1,105.17. Notice that when you compound continuously, you actually make more money, which makes sense because you're getting interest quicker because it's compounding and accumulating faster. This is called the effective rate of interest. Essentially, the only way to change how fast your money grows is to either compound more often or to increase the rate that they give you for the interest. So to figure out your effective rate, which they call R sub E, of an investment earning an annual interest rate of R, you have to use this formula. So if it's compounding n times per year, and by the way, what this is actually telling you, just because this is actually a good thing to know for like real life, this effective rate tells you what rate in simple interest does the same work that your compound interest is doing. So it's kind of like APR for credit cards and stuff like that, where or if you're borrowing money for a car, you always notice that the APR is higher because that's the annual percentage rate. That's because annual percentage rate is a simple interest rate that has to work harder or have a higher rate to do the same amount of work as a compound interest rate. So that's what we're looking for here. And if it's continuous compounding, there's a different formula. It's e to the r minus 1. So let's look at my example here. By the way, this should look familiar because this has to do with the actual compounding formula. So this guy right here says, suppose you want to buy a 5-year certificate or a CD. You visit 3 banks to determine their CD rates. American Express offers you 2.15% annual interest compounded monthly. And First Internet Bank offers you 2.2 compounded quarterly, and Discover offers 2.12 compounded daily. Determine which bank is offering the best deal. Because they're all compounding at different intervals of time, it's really hard to know which interest rate is better unless you convert them all to simple interest, which means we're looking for the effective rate. So let's do American Express first, and it would be 1 plus 0.0215. It's being compounded monthly, so that would be divide by 12. The n is also 12 again, and then minus 1. So we're going to get an approximation for that. Let me erase that. Move this down a little bit. Okay, so parentheses 1 plus 0.0215 divided by 12 raised to the 12th power. Oops. Won't let me do that. I'll have to re-enter it. I was still in second mode. So 1 plus 0.0215 divided by 12, close parentheses, raised to the power of 12, and then minus 1. This is 0.0217, which equates to about 2.17% simple interest. Okay. And then we want to do First Internet Bank next. They are offering us 2.2%, so that'd be 0.022 compounded quarterly. So notice they raised the interest rate, but they lowered the amount of times that they're compounding. So that is going to affect how this compares to the other one. So because both of those things are part of the situation of what makes the money grow. So this is 1 plus 0.022 divided by 4 raised to the 4th power, and then minus 1. So that's 0.0222, which is about 2.22%. And then lastly, we have the Discover. which is doing 2.12, which is the lowest rate, but they're compounding daily, which is 365 times in a year. So it's a really big exponent. So 1 plus 0.0212 divided by 365, close parentheses, raised to the 365th power, and then minus 1. So that would be 2.14% or 0.0214. So the one that's offering the best deal is actually the one that has the higher interest rate. It's compounding quarterly, which is less time, but having that extra 0.05% actually makes a difference. So that's why when you're negotiating for cars or houses or anything like that, interest rates really do matter. So this one would be the best choice. For present value, I just want to go over this. If they ever have, this is when you're solving for P instead of A. So remember our formula was A equals P parentheses 1 plus R over N to the NT. If you want to solve for P, essentially you just divide that big blob of parentheses to the other side. So this is how you would solve for P. For the PERT formula, you divide the ERT to the other side. So just in case you needed to rewrite the formula, that is possible. So if I want to know what annual rate of interest compounded annually is needed in order to double an investment in 5 years, so we don't know how much money we have. And in fact, it doesn't even matter. What determines what your time is for doubling your money is your rate. So let's just pretend that we have $1,000. If we want that to double, which would be its future value, we would say we have $2,000. This is being compounded annually, which would mean that N is once a year. And we don't know the rate yet, but we do know time is 5 years, so R is the question. So if we plug into our formula for all of the compounding stuff, this is 2,000 equals 1,000, 1 plus point, well, we don't know the R, sorry, R over 1 to the 1 times 5. Okay, so I would divide the 1,000 over first. So notice that just makes this 2. This is 1 plus R to the 5th. We want to try to solve for R, so we need to get rid of that 5 as an exponent. One way we could do that would be to take a log, but that doesn't always make that easier. You could just raise everything to the 1/5 power. So what that would do is cancel out that power right there. So then now I have the 5th root of 2 essentially on this side, because this is the 1/5 power, equals 1 plus R. So R equals the 5th root of 2 minus 1. So we would want to figure out what that is. So 2 I'm not sure if that's the right way to do that one. Let's see if it's the other direction. That doesn't look right either. Let's see. Trying to test the root thing on this calculator is a little funny. If I wanted to do the cubed root of 27, okay, so you do enter in, so that's how this has to work. Sorry, this calculator is just not my typical one. So I need to enter in the number first and then tell it what root I want. So I'm doing a 5th root, and then we're subtracting 1 from that. So it looks like our rate is 0.15 if we round to 2 decimal places, or about 15%. So you'd need a pretty high rate if you wanted to double your investment in 5 years. So what if we wanted to do this for continuous? How long will it take this or any investment to double if the value it earns is 5% compounded continuously? So for A part, we're looking at our PERT formula. Again, let's assume that we had $2,000 at the end, which means we started with 1,000 because we're doubling. E, and we don't know R, and T is still 5 years. No, it is not, sorry. I'm not reading my question carefully. We asked how long, so we don't know T. We do know the interest rate, so 0.05, then T. Okay, because this is in an exponent, anytime a variable shows up in an exponent, logs need to be used, especially if you can't get the same base. So I'm going to divide the 1,000 over first. So that would be 2 equals e to the 0.05t. I'm actually going to use natural log because I have a base e. And there's a reason for that. So let's do natural log. Then we can pull this power by using the log rules to the front. So this would be natural log of 2 equals 0.05t times natural log of e. If you type natural log of e in on your calculator, you'll notice that this actually equals 1. That's because it's a base e and it's to the e. So e to it first power equals itself. So that means that guy actually goes away. That's why we wanted to do the natural log if there's a base e. So all I have to do to finish this is divide by 0.05. So natural log of 2 divided by 0.05 will give me my approximation for the number of years it's going to take to double. So natural log of 2 divided by 0.05 is about 13.86 years. So that's a long time. How long will it take to triple? Well, do you notice that this always ended up being a 2? If you're doing tripling, that means the other side's going to end up being 3, like having $1,000 become $3,000. So if we just need to recreate this, essentially this is going to solve the same way, except we're going to have natural log of 3 divided by 0.05 at the end. So 3 natural log divided by 0.05 is 21.97 years. That's how long it would take to triple our money at 5% compounded continuously. So that's a long time. And it doesn't matter how much money you started out with. If you'd started out with $1,000 or $1 million, because interest and is the main thing changing how long it's going to take, that is what's going to determine this for us. So the interest rate's pretty low here, so it's taking a long time to accumulate wealth. Okay, so 6.8, this is the last piece of the word problems, is about exponential growth and decay. There's this generic formula that says that this is the amount after time has passed equal to the initial amount times this rate right here. This is our factor of decay or growth, depending on which way it's going. Remember, a growth function looks like it's going uphill. A decay function looks like it's going downhill. A model that gives the number n of cells in a culture after time has passed in the early stages of growth is that same type of formula, so they're calling it n now. N sub 0 is the initial number of cells. K is a positive constant that represents the growth rate of the cells. So this K is going to be a percentage of growth. So we're going to work through this example. A colony of bacteria increases according to the law of uninhibited growth. If n is the number of cells and t is the time in hours, express n as a function of t. So that would be, for A part, n of t equals n sub 0 e to the kt. It's just our formula. Part B, if the number of bacteria doubles in 3 hours. Okay, so that means that, let's say n sub 0 is 100. So now n of t would be doubling that, so it'd be 200. So we're just making up an example where something is doubled. 3 hours is our time. we want to find the function that gives the number of cells in the culture. So we need to plug in what we know. So this is 200 equals 100 e to the k times 3 for hours. When they want us to write the final function, they don't want us to give them everything. They want to know this growth rate. So we do need to solve for k. So because k is in an exponent, we're going to need to do a natural log or a log. So I'm going to divide by 100 first. So this is 2 equals e to the 3k. Take the natural log of both sides so that the 3k can come down to the front. Remember, natural log of e is just a 1, so all we have to do is divide by 3. So let's get an approximation for how our function is growing. Oops, that was supposed to be natural log of 2, sorry. Natural log of 2 divided by 3. So 0.23. That means that our cells are growing at a rate of 23%. Essentially, that's kind of like their growth rate. So the formula for this would be n of t equals n sub 0 e to the 0.23 times, I guess we don't need the 3, we can leave it as t, because we want this model to be able to function for multiple groups of hours. So that would be that guy. For C part, it says how long will it take for the size of the colony to triple? So we're looking for time now. So now that we have this, we can plug in. So tripling means that you get 3 equals just the e to the 0.23t, because remember the n sub 0 and the n of t, when you divide, if this was 100 and this was 300, when you divide over, you just get 3. So this would be natural log of 3 equals 0.23t natural log of e, which that is a 1. So what I did there was I actually took the natural log and pulled the power to the front all at the same time. So natural log of 3 equals 0.23, or excuse me, divided by 0.23 equals t. It's hard to talk and write. So this is 3 natural log divided by 0.23. Looks like this is 4.78, and this is in hours. So wow, this colony will triple itself in less than 5 hours. And then how long will it take the population to double a second time? That is to increase 4 times. So we're quadrupling essentially. So we would say that this would be 4 equals e to the 0.23t. And natural log of 4 divided by 0.23 is going to equal t again, kind of bypassing some of the steps since all of these work out the same way. So natural log of 4 divided by 0.23 is 6.03. And that is still hours. So this one is decay. Essentially, decay means that instead of something growing, it is getting smaller and dying off. That happens a lot with radioactive materials. And it's the same type of setup. So this one is traces of burned wood along an ancient stone tool in an archaeological dig in Chile were found to have contain approximately 1.67% of the original amount of carbon-14. If the half-life of carbon-14 is 5,730 years, approximately when was the tree cut and burned? Okay, so this has got a lot of words, science words we have to talk about. By the way, notice that K has to be less than 0 because we are not increasing our colony or our group of things, we're decreasing. K has to do with your rate of growth or decay. So for us, it's a decay rate. So when we write this, R is 0.0167, but because this is a decay function, it's negative. So that's that. The half-life, let me explain what a half-life is. Half-life, in case you've never played that game, is when A of t is half of A sub 0. So that's what that means. And we know that the half-life is going to be that t is 5,730. And we want to know when was the tree cut and burned. So we don't know the initial amount. But we do know the half-life. So, all right, let's use this information first. So 1/2 of a sub 0, because that's going to be our a of t, equals a sub 0 times e to the, let's see, k for us is, I called it r. We're going to leave that alone right now, and let's actually see if it works out to be this guy right here. And the half-life happened at 5,730 years. So let's see, this is, the a sub zeros are going to cancel out when you divide. This is 1/2 equals e to the 5,730 k. Take a natural log of both sides so that we can bring that power to the front. And that's a 1. And then we're going to divide by 5,730. So 0.5 natural log divided by 5,730 is actually, ooh, that's very small. Negative 1 point, or actually, and that's to the EU. This is scientific notation. So negative 1 point, I'm going to write it down first, 2097 times 10 to the negative 4th, I believe, which means this needs to be moved 4 places to the left. And that would still be as a number. Oops, so this negative goes out front now. And we would still need to convert it to a percent.